You ever look up at the sky and just wonder, what is all that? Because it's so much more than just blue air, right? It's this invisible, multi-layered ocean that, well, protects us, gives us all our weather, and pretty much makes life itself possible. So, okay, let's get into it. Let's dive into this incredibly complex and beautiful system.
Wow, just look at this. The northern lights, just dancing on the very edge of space. I mean, this spectacular show, it's a direct result of the sun interacting with the tippy top of our atmosphere. It's just such a powerful reminder that this blanket of air we're all living under, it's not static at all. It's a dynamic, powerful shield.
All right, so here's our flight plan for today's journey. First, we're going to cover the basics, our protective atmosphere. Then, we'll start climbing through the layers, from the troposphere where all the weather is, up through the stratosphere. After that, we hit the really extreme stuff, the fiery and frozen layers. And to wrap it all up, we'll look at the great energy exchange that powers the whole system.
Okay, first things first, where did all this air, the stuff that keeps us alive, even come from? Because it wasn't always here, not by a long shot. Earth's atmosphere has this really dramatic history, and it's evolved right alongside life on the planet.
Believe it or not, Earth has actually had 3 totally different atmospheres. The very first one, it was mostly light stuff, hydrogen and helium, and it got completely blasted away by the early sun's intense solar wind. Poof, gone. The second one was literally forged in fire. Volcanoes all over the planet just spewed out gas, creating a brand new, much denser atmosphere. And the third one, the one we're breathing right now, well, that was made by life itself. Early organisms started that whole photosynthesis thing and began pumping out the oxygen that changed everything.
Okay, here's a fun fact that might actually surprise you. We're always talking about oxygen, right? It's what we need to breathe. But look at the actual numbers. It's only about 21% of the air around us. The vast majority, a whopping 78%, is actually nitrogen. And then everything else, all the other gases combined, they're all crammed into that tiny little 1% sliver.
All right, let's start our ascent. First stop on our journey up is the layer we all live in, the troposphere. And this is where it all goes down. Clouds, rain, storms, literally all of our weather happens right here.
Okay, this graph right here is going to be our roadmap for the climb. Now, it might look a little complex, but just focus on 2 things with me. The vertical axis is altitude, how high up we are. We're starting at the very bottom, right here in the troposphere. Now, see that red line? That's tracking temperature. Just watch what it does as we go up through this first layer. See how it moves to the left? That means it's getting colder.
So that drop in temperature actually has a name. It's called the lapse rate. The technical term is a positive lapse rate, which I know, sounds kind of weird, right? Positive sounds like it should be getting warmer. But all it means is that as your altitude goes up, the temperature goes down. Just think about it this way. Why are mountaintops so cold? It's because they're way up high, far away from the ground, which is what's actually heating this layer of the atmosphere from below.
And here's the key thing. This isn't random. There's an actual average, a standard lapse rate. For every single kilometer you climb, the air gets about 6.5 degrees Celsius colder. It's like a fundamental rule of the troposphere, the layer we call home. But get ready, because that rule, it's about to be completely broken. Okay, we've punched right through the clouds and all that weather. Welcome to the stratosphere. And up here, well, everything we just learned about temperature gets flipped completely upside down. So here's the big twist. In the stratosphere, as you go higher, it doesn't get colder, it actually gets warmer. This complete flip-flop is called a temperature inversion, and it creates this super stable layer of air. That's exactly why jet planes love to cruise up here, to get high above all that turbulent, bumpy weather down in the troposphere.
So, what's going on? What's acting like a giant heater up here in this layer? Why the temperature flip? The answer is one very special little molecule, a type of oxygen called O3, which you probably know better as ozone. Think of the ozone layer as Earth's natural sunscreen. It's up there absorbing the sun's most harmful ultraviolet or UV radiation. And as it soaks up all that energy, it releases heat. That's what warms the stratosphere and creates that crazy temperature inversion we were just talking about. And this is actually a fantastic success story for science. When we figured out that certain chemicals were eating away at this layer, the world actually came together, banned them, and now this critical shield is slowly but surely healing itself.
Okay, let's keep climbing. We are now entering the realm of the truly extreme. The next 2 layers up, the mesosphere and the thermosphere, this is where we get into shooting stars and those shimmering auroras.
So let's break down these next two layers. First up, you have the mesosphere. This is basically our planetary meteor shield. It's where most of those fiery streaks we call shooting stars burn up from friction. Then, right above that, you get the thermosphere. This is a region with so much energy that it's home to both the International Space Station and those incredible auroras.
And the temperatures up here are just wild. The mesosphere is the absolute coldest place on Earth, dropping all the way down to minus 100 degrees Celsius. But then you go just a little bit higher into the thermosphere, and it gets incredibly hot because it's absorbing so much solar radiation. But it's a weird kind of heat. The air is so thin that if you were there, you wouldn't actually feel warm. This layer is also full of these electrically charged particles, ions, that we used to use to bounce radio waves all around the globe.
And then, at the very top, we have the exosphere. This is pretty much the final frontier. It's the last wispy layer where there are so few air molecules that it's barely an atmosphere at all. This is where our world just gently fades away into the vacuum of space.
All right, so we finished our tour from the ground all the way up to the edge of space. Now, I want you to zoom out with me, because all of these layers, the weather, the crazy temperature changes, all the chemistry, it's all driven by one single thing, a massive engine that's powered by the sun.
To really get a handle on how this engine works, we need to talk about a concept called albedo. Honestly, the easiest way to think about it is just shininess. How reflective is the surface? Something with a high albedo, like fresh snow or a mirror, reflects a ton of sunlight. And something with a low albedo, like a dark road or the ocean, absorbs most of it.
And you can really see the massive difference here. Fresh, bright white snow has a super high albedo. It reflects up to 90% of the sunlight that hits it. But the dark surface of the ocean, totally different story. It has a really low albedo, so it absorbs most of the energy and only reflects about 10%. And this one simple difference is absolutely fundamental to how our planet's whole climate system works.
And all of this feeds into something called Earth's heat budget. And it really is like a budget, a delicate balance of energy coming in and energy going out. So let's just follow the numbers, nice and simple. Imagine 100 units of energy show up from the sun. Right away, about 35 of those units get reflected back into space by clouds and those shiny high albedo surfaces. So that leaves 65 units that get absorbed, warming up the land, the oceans, the air. Now, for the planet's temperature to stay stable, those same 65 units have to eventually radiate back out into space. What comes in must go out.
But as that heat tries to escape, it doesn't get a completely free ride out. It runs into certain molecules in the atmosphere. Yep, greenhouse gases like carbon dioxide and methane. And they act just like a blanket. They trap some of that outgoing heat, which keeps our planet at a nice, comfortable, livable temperature. Seriously, without them, Earth would just be a frozen ice ball. So, when you think about it, from its fiery, volcanic birth to the super delicate energy balance that runs it today, our atmosphere is just this incredibly complex system. It's a finely tuned engine that has made it possible for life to thrive here. And that really leaves us with one crucial, final question to think about. What happens if we start changing that formula?